Welcome to the fourth video of our series Rudimental Fields. Today we will continue to pave the road to the discussion of Galois theory. And our first item is to define the isomorphy of two extensions. So we start out with two extensions like so, and they are said to be isomorphic if there's an isomorphism between the overfields EI, say phi, that takes the base field number 1 to base field number 2. And of particular importance is when F1 and F2 are the same field. And this should come as no surprise, right? That certain algebraic properties of extensions are preserved under isomorphisms of them, such as algebraicity, simplicity, finite degree, infinite degree, and etc. This is one of the particular cases of importance where the base fields are both equal to the same thing, and the isomorphism between the overfields extends the identity automorphism of F, in which case phi also constitutes a linear transformation between the two vector spaces E1 and E2, hence the term F isomorphism. This is a simple but important tool that we covered in more generality in the past, I remember, where we had two rings, basically, and a ring homomorphism, which induces a ring homomorphism between the corresponding polynomial rings. Here we have fields, and then this is assumed to be a field isomorphism, in which case the induced map is also a ring isomorphism. And the rule that defines it is this. Our main aim here is to relate sets of roots of a polynomial over a field F in various extensions of the field F. And we want to relate them to each other by way of F isomorphisms, hoping at the same time to be able to answer questions such as the following: whether F can be completely factored with all roots distinct in one extension of F, whereas it is factored with repeated roots in another extension. Well, to approach this question, we first identify our constraints of necessity and start with the most particular case, most special case of extensions where both the base fields and the overfields coincide. So you have a field extension F in E and a polynomial F over the base field capital F, and assume the set of roots of F in the field E is omega. Then any F automorphism of E when restricted to omega is a permutation of omega. And since the same thing applies to the irreducible factors of F, it turns out that an F automorphism of E cannot take a root alpha of one irreducible factor, say U, to a root beta of another one, say V, unless they have alpha and beta are common roots of both U and V. So this argument is basically a factor that confines our attention to irreducible maps, irreducible polynomials. But another question pops up here, which I will pose later on as an exercise. But let me mention it here too. Is it even possible for two non-associate irreducible polynomials to share a single root, even a single root? Is it possible? We give our result, our key result, in as broad terms as possible. So we take two field extensions and elements alpha I in the base fields fi, and two irreducible polynomials which are mapped to each other by the induced isomorphism of two fields, the base fields. Okay, so under these hypotheses, there is a map, there is an isomorphism of rings, but in this case fields because of algebraicity, right? That extends phi and maps one root alpha 1 to the other. Well, I guess we should simply visualize this same situation when the base fields are the same and the overfields are the same too. This means we would be, phi would be mapping one root of an irreducible polynomial f to another root of it. So we could always find f automorphisms between these f isomorphisms between these extensions doing that, one at a time though. The proof is easy. I'll just indicate a sketch for the proof. We have this diagram immediately available in the first place, where phi hat is the usual thing, the isomorphism induced by phi, and pi I are the evaluation maps. Now the role of the irreducibility of fi appears here, factors here, where the kernel of the evaluation maps is generated by any irreducible polynomial having alpha i's as their roots. In which case, and in this case, we have alpha fi's for that purpose. So this guy generates the kernel of the evaluation map. And then we go back. We simplify this diagram by composing the pi 2 and phi hat, and get this diagram where this guy's kernel is equal to this guy's kernel. This is a very common scheme in algebra where the viewer will realize that it's possible to find an isomorphism connecting the two ends of this triangle and completing the diagram commutatively, meaning phi 1, the composition phi pi 1 will equal pi 2 phi hat. And it's easy to check such details as phi being an isomorphism, taking alpha 1 to alpha 2 as desired. Again, here's a special case. In the special case of a single extension where alpha and beta are roots of the same irreducible polynomial. This means there's an f isomorphism between these two extensions mapping alpha to beta. And the next question that arises is this, although we don't mean to pursue it right now, or maybe not any time in the future, but it's a good question to attempt and try to understand the difficulties surrounding these situations. The question is, okay, when we can, as this discussion shows, we can always find f automorphisms between these things mapping or connecting one root to the other. What's the best we could hope for? Well, the question is if it is possible to find f automorphisms of the extension of the field f by all roots of, namely the set omega, by all roots in E of the polynomial f that affects any permutation we choose. That would be the best scenario. So is it possible? Next, we define what it means for a non-zero polynomial to split over a base field f. It means it's either a constant, the polynomial that is, or it can be factored completely into polynomials of degree 1 each, like so. The question that we aim to answer is this. Yes, f may not split over f readily, but then can we guarantee that we can find an extension of f over which f splits? Is there always an extension over which f splits? The answer is yes, and this can be done step by step using the lemma or instrument that we just proved. If f doesn't readily split in fx polynomial ring, then it has an irreducible factor g that doesn't split over f. So the question is, if you want to split g first in an extension, what is the best place to look for such a root? Well, such an extension would contain an isomorphic copy of this quotient, right? As g would then be an associate of the minimum polynomial of alpha over f. So then this being the immediately available suspect, we work on that one and work it out that it is in fact the one we are looking for. And the details are again left to the reader to verify. So basically, since g is irreducible, this is a field and it contains this copy of f, and the corresponding copy in f of g, which we denote by g bar, has this guy as its root, which is our alpha. Now, that takes care of one irreducible factor that doesn't have a root over f. If you iterate this process until you exhaust all the irreducible factors without roots in each step, namely those of f, then at one point you will have exhausted all of them and finished the proof. Now we have a name for the minimal such extension, namely if E is an extension of f over extension of capital F over which f splits, and E is generated by f, by the field f, and the roots of f in E, then it is called the splitting field of f over the base field f. Here's an important exercise we will be using without proof, and the proof of which we leave to the viewer. Any two splitting fields of f over capital F are isomorphic via an f isomorphism. And this answers a question that we posed before, namely whether a polynomial can be completely factored with distinct roots in one extension of f and with repeated roots in another, and the question's answer is negative. So it's not possible to do that. So just take two splitting fields, take the unique splitting field of f over capital F in each extension. The exercise tells us there's an f isomorphism between them, which maps the two sets of roots to each other, and thereby establishing the fact that their sizes must be the same. Okay, so this answers our question. And the next question, if we raise the stake a little bit higher, the next natural question is if we can find an extension of capital F over which all polynomials over f split simultaneously. Those of you will realize by now that we are pointing at what's called an algebraic closure, but this is next time. Thanks for listening.